All right, well, welcome everyone to week one. It's good to see you all again. Um, I know this is a way to start very vigorously. We're going to go through 4 sections today, and I'm going to try to cut it down to about 60 minutes. All right, that way we'll have about 60 to work on our group quiz together. All right, but this very first section is the whole chapter actually is about functions. All right, so the first thing we're going to do is obviously define what a function is. And so we're going to first talk about the relationship. If you have a relationship, in order for it to function, for every input, there has to be output. All right. We like to call that one-to-one. Okay. So in order for there to be a relation, which is just a set of ordered pairs, we're going to talk about all those inputs and give them a name, and all those outputs and give them a name. You guys should be familiar with that. That's domain and range. So this right here, these curly braces denote what is called a set, okay, a list of things, and they've given us a bunch of ordered pairs, right? And those pairs are together by these parentheses where we have some X and some Y. And when I put in to that relationship, whatever it is, the number 1, what comes out is 2. When I plug in 2, I get out a 4, and so on. So that's the relationship that we're talking about, where the domain would be all those X values, so 1, 2, 3, 4, and 5, and the range would be all those outputs, the Y values, 2, 4, 6, 8. Who do we abbreviate? All right, so those are the things. Sorry, Barry, I didn't like that one. He's like, oh shoot, I'm still on. These are the things that we're going to be mentioning, referring to, so make sure that you understand which ones are the inputs, and therefore we will call the independent variable, and the outputs, which is dependent on that input. Okay, domain and range are what we call that whole set of things. Okay, like I mentioned, that function, in order for a relationship to function, you have to have what is called a one-to-one relationship. Okay, I'm not speaking from experience, okay, but that's the best way for something to function. And you can think about like a vending machine. If you select a certain thing, you want that one thing to come out, all right? Or maybe not, you'd rather have 2 or 3 things drop. But if you own that vending machine, in order for it to function properly, when somebody puts in the value that they want for it to function properly, they need to get that one thing out for their money. Okay, so that's what we're talking about for a function. So there's a little how-to and what we call function notation. Okay, input values, aka domain, output values, aka the range. And like we said, if each input leads to only one output, then we can upgrade that relationship to a functioning relationship or a function. Okay, if it's 2 or more, no good, right? And the way that we denote that is, instead of having an X and a Y, our input and output, our domain and range, we will be able to replace the output and let you know that it is a function of X, or as you guys know it better as, f of X, right? But that still is going to represent our output, our Y values. So instead of having Y equals 3X plus 2, we can, if it's a 1 input, 1 output relationship, replace that and put f of X. That gives it more power, all right? So if I was to give you something like this, could be any letters. Instead of Y, I'm going to put N. Instead of f of X, I'm going to put f of Y. And I'm going to tell you where N represents the number, that's why they're using N, of police officers. And I'm using Y to represent the years. What would this mean according to these things? What would f of 2005 equals 300 represent? Well, if you write exactly what I told you right over here, the Y represented the year, and the N The output represented the number of police officers for that year in said city or town. Okay? So things that, again, we should be familiar with. When do we use functions? Most situations like this. Okay? So we don't have to do this. I just wanted to show you an example. You guys tell me to speed up, slow down, go over it more, expand. It's totally up to you guys on how fast we go through these. All right? But you need to know that they're asking you to evaluate a function of x by replacing anything with x. Okay? So in this case, I'm going to replace everywhere there is an x with a 2. And then I'll evaluate and tell you what I get out. So the main thing that you guys are going to have to do with these is basically just rewrite them as f of something is equal to that thing squared plus 3 times that thing minus 4. But that looks a little unfinished, doesn't it? That's why we use the x as the unknown, the variable, the thing that can vary and change. But all we're going to do is replace that x everywhere we saw one. And then simplify this to get a easier form. So again, if you guys want to do any of these, let me know, but f of 2, all I do is plug in a 2 there and there. Order of operations, exponents first, because I can't do anything inside the parentheses, and then multiply before I add or subtract. So that would give me a 6, and then minus 4, 4s would cancel. When I plug in 2, I get out a 6. Does that prove that it's a function? That one-to-one relationship? No. You would have to check it for every single thing. And that's the power of them already telling me that that is going to happen by writing f of x. They're already telling you that we have a function with x's in it. Okay? Now the ones obviously that are a little bit more challenging is when there's more than just a single thing there, like a plus h. So how does that change? Well, not much actually. If I'm going to do this, it's going to be the same thing. But this time, we're going to be plugging in an a plus h to my function. I'm inputting that a plus h everywhere I see it. Now, again, the one thing that you're going to have to make sure that you know how to do is the order of operations. And that means that when you see this squared term here, you're squaring this, whatever's in there. That does not mean you just square the a and square the h. And that's the most common mistake with students in calculus, because you will be doing things like this a lot, especially at the beginning. Okay? You actually have to take the a plus h and square it, which means foiling or distributing to get your a squared plus an AH and another AH, which means I have 2 AHs, and then my H squared last. You see, if you just squared the A and the H, you would completely have left off that middle term. And again, that's one of the most common mistakes within these types of problems. And that, unfortunately, would be my answer for that. Of course, we want to try to simplify to make it look simpler and be simpler to work with, but sometimes there are no like terms within this. So don't force it. So if you notice, that is exactly what this is here. That's my f of a plus h. That's what would be that part. If I'm going to subtract f of a, hey, that's what I did earlier. So I'd have to take all of that and I'd have to subtract what I found from all of this, my f of a was, which was the a squared plus 3a minus 4. Now remember, when you're subtracting f of a, an entire function, that means you got to subtract all of this. So include the parenthesis there to make sure that you do distribute. and don't just subtract the first thing that's there since you didn't put it. And when you take f of a plus h and you subtract f of a, what do you expect to happen?
For some to cancel out.
What? What sum? What stuff?
The a squared, the 3a, the -4.
Yeah, I would anticipate the whole f of a part would cancel out since I had it and more there. So if you check that out, the a squared would cancel with this a squared when I subtract it. The 3a would subtract with this 3a. And the -4, when I distribute that negative here and made it a +4, would also cancel out. And notice the only things that I'm left with are what? The things with h in them, that little additional part that we added over here. So that will give me the 2a plus h squared plus 3h. And notice that it had the whole thing over h. Does that mean I just get to cancel this h and that h? No, very good, because this whole division bar meant that they wanted you to divide this h into all of them. And so all I'm going to do is simply take and factor out an h out of this, this, and this, which would leave me with 2a plus h plus 3. And now I can go ahead and cancel that h in the denominator with that one, because I know anything divided by itself is 1. And that, my friends, would be the answer to letter D. Now, it seems like a mess, and you're absolutely right, but this is one of the most important concepts that you will start out calculus with. You will actually name this whole thing here, which let me clean it up a bit. This is called the difference quotient. And it will be the basis of the entire first semester of calculus. We will name it something even better when we introduce this thing called a limit, and it's called a derivative. Okay, but that's just giving you a preview of some of the things that you algebraically will have to do many times over in calculus, and therefore in this class. Okay, all has to deal with functions. Now, instead of giving you the algebra, I can also give you the geometry behind it. I can give you a graph like this, which you guys probably recognize is called a parabola, a quadratic form of x squared and some friends. So if I ask you to find f of 2, you should know what that is asking for and be able to provide it. Or if I ask you to solve for x, and therefore I give you the y value. Okay, and if you're ever not sure about these, just write, I remember that f of x is equal to the y. That's what Alan told me. And therefore you will know, hey, this is giving me the x, and it wants to know the y value. And as long as you know that I gave you the x is 2, then you will go 2 to the right, and then you will either go up or down until you hit your graph and give me what comes out, that output. So this first one up here, what is f of 2?
1.
Good, pretty easy. When x is 2, I get out a y value of 1. But you need to recognize that the second part is giving you the f of x is equal to, they're giving us the y is now 4. But be careful. What does that mean we could have?
More than one answer.
Very good. Where is y4? Well, I know this is the y-axis. And I know if I go left or right, I actually hit in 2 spots. So what x value? And what x value?
-1 and 3.
Does that mean it's not a function? Well, you guys should know it's already telling us that this thing is a function by the way that they've written it. So we'll have to talk about that one-to-one input to output thing in a minute here. But if I put in a 3, what do I get out? What's the only thing I can get out?
4.
How many?
1.
Only one thing. So when I plugged in 3, look, I got one thing out. When I plug in -1, one thing out. So notice I keep drawing for any x that I select. I kept going up until I hit it, my graph, and notice it only hit at one place. Anybody know what I'm getting at here? How do we test whether a graph is a function?
The vertical line test.
Now, hopefully you understand more why. Because literally, we are testing any and every x for one and only one y value. Okay? So that's what the vertical line test helps us to tell whether or not something is or is not a function. And what it's really testing is this one-to-oneness that we've been mentioning. Okay? No matter where I draw a vertical line on this, I would only hit one place. This, there's only one line I could draw that I could only hit one place, and that's at the vertex. Everywhere else, fail, fail, fail. Fail, fail, fail. Only 2 places here that it wouldn't. Okay, but it has to pass for all. So the difference between being one-to-one and seeing if something is a function and being a one-to-one function is that the one-to-one function functions both ways. To see if something is a function, you check the input to the output. But a one-to-one function goes both ways. Input to output, and then output to input. Is it a one-to-one correspondence both ways? And as we saw here, no, it would not be. Is this a function?
Yes.
Yes, they told us it was. Is it a one-to-one function?
No.
How do you think we could test that?
Horizontal line test.
Very good. Because now we're testing it the other direction. The output to the input, the y to the x. And so instead of doing the vertical line, which tests all the x values for a y, now we're going to do the other direction, which is all the y values, seeing how many x's or those inputs we would have. Okay, so that's the difference between being one-to-one and being a function and being a one-to-one function. I know that's confusing because they're so similar. So I'm trying to make sure that you understand that. Okay, now we can make this be a one-to-one function. Anybody want to know how? Anybody have an idea how? Better yet. No, nothing. That's disappointing. How about if I got rid of the whole left side? You guys know if you get rid of the whole left side, then you're all right. You get it? All right. No? No, but the reason if I got rid of 1/2 and I just chose the left side from the vertex, now would it pass?
Yes.
So we can put what are called restrictions on the domain and force functions to now be more powerful and be one-to-one functions. Okay? And that will get us into those inverses and things like that. So again, vertical line tests to see if something is a function, horizontal line tests to see if it's a one-to-one function. right? That's it for the first section. That's the synopsis of everything. Now we're going to get a little bit more in depth into functions and talk about their inputs and outputs in a little bit more detail. Domain and range. And with that comes this thing called interval notation. So remember I talked about in order for something to function, it has to have one input and one output come out. Think about that vending machine. Okay. In order for us to tell them what things that we can input so that it does stay with that function notation, we will use, rather than listing everything because we can't, we're going to use this thing called interval notation. And do you guys remember the difference between the parentheses and the brackets?
So greater than and equal to, or
Very good. If we're talking about a number line and all the things that do work that we can put in to this function and we'll get something out, then we talk about the closed dots versus open dots. And for us, if you just take the half of the first letters, you'll see that's exactly what we have, is a parenthesis or a bracket. That's my fun little way to help you guys remember open versus closed. Okay. Open dots mean that we do not include it, but it goes right up to that value. Closed dot means, you know what, we're going to go all the way up to that value and include it. All right. So here's some of the ways that we can see that on a graph. So whether they put an open dot here or they put the parenthesis, that's letting you know not this value of A, but everything to the right of it to infinity. And so that's how we would write it. Now notice every single one of the parentheses are around the infinities. Because what's infinity? I like that answer, Barrett. We don't know. All it is an idea. There's not a biggest number. If you guys were to tell me what your biggest number is, and then I went and asked a 3-year-old, do you think their big number is going to be like 99? And yours is what? Anybody got a real big number? How about a Google? That's actually a number. They stole the name. That's how you spell Google, as the number. They just added the E at the end. All right. Google is a 1 with a million zeros after it. Anybody want to do me one better? All you got to do is add 1. A Google plus 1 is bigger. And if you add 1 to that and 1 to that and 1, you get the idea. So that's what infinity represents, is the furthest right you can go on the number line. That never ends. How do we go to the left? We throw a negative on it because we know 0 splits the positives and the negatives. Okay, so pretty cool stuff. Again, just a quick reminder of open versus closed and all the different forms that we can have to represent either a solution set or the domain and range, things that we could plug in and or get out. Okay, now obviously we'll see a couple different ways to do this. So that's all this stuff is basically talking about. And I'll just highlight it real quick before I run through it, but that's why I wanted to record these in case you guys want to pause and read through or write any of this stuff. But if it's written in equation form and they ask you to find the domain, you're just looking for all the input values. Okay, what we're going to look for, because there's an infinite amount of numbers, we're going to look for the things that don't work, the restrictions only. All right, so to tell them all the things that we can input, we're going to look for the things that we can't. All right, and we'll use that interval notation when possible. So if you have a fraction, what would we be looking for to find the domain? All those input values. What restrictions would we have? Well, that's when the denominator is equal to 0. We cannot take a number and divide by 0. Doesn't work. So those are our restrictions, okay, when we have a fraction. What about with roots, radicals? Well, it has to be even because there are no restrictions with odd. And for these, we have to exclude numbers that result in a negative number inside the radical, or the fancy term radicand. Okay. Every once in a while, we'll make it really difficult and we'll throw a root and the denominator of a fraction. So then you got to account for both scenarios. Okay. So if I was to give you this line graph, could you give me the answers or domain or whatever this pertains to? Where would you start? How do we read graphs? How do we read a book? Left to right, top to bottom. So the same thing for this one. There's only left and right because it's only the x-axis. We'll get to when there's a y as well. But what is the domain on this then? Where does it, quote unquote, start? Is it at -5?
Negative infinity.
And beyond. Very good, Julian. That's right. That arrow represents something very, very important. It goes on forever. So we're going to start at -infinity. And are we going to include infinity ever and put that nice bracket, give it a nice big hug?
No.
No, very good. Parentheses around infinities always. Because we cannot tell you what infinity is, we cannot include it. Okay. We'll put comma to represent all the things until we get to what?
-2.
And then we will give it a nice big hug because it is included. It's a closed dot. But then you see we have this void here. So we need to unite the other set of numbers that go from here to here. And what we do to do that in math is we use this fancy U called the union. For anybody that's gotten married or gone to a wedding, that's what they call it when they're bringing two people or families together. It's called a union. Same thing here, all right? Just don't put the little U line. That's more English, okay? That's the symbol we use for union. And then this one starts at -1, which is included, all the way to 3, which is excluded. And you guys know if it's a quiz or a test and you have multiple choice questions, what are they all going to look very similar to? That, which means what do you have to really pay attention to?
Brackets.
Yeah, the parentheses and the brackets, and make sure you select the correct answer. All right. So again, pay attention to that. Those things matter. How about here? Could you guys give me the domain and then the range? What is the domain looking at? Keep it alphabetical. The D is the X, R is the Y in order. Okay,
-3.
good. We're going to go from left to right and we're going to read this thing. Where do we start?
-3.
But is it included?
Nope.
0.
Good. It's not included. That's why it's got this open dot. But what about -2.9 and -2.9999999? All of those. That's why we don't say anything other than start at 3, but not 3. Anything to the right, all of this for my x's until I get to what?
1.
1.
And is that one included?
Yes, so you put brackets.
There you go. Now, How are we going to do the domain? Excuse me, the range. We already did the domain. How are we going to do the range? Now we're looking at the y values. And just like here, we went from left to right because it's smallest to biggest. What's smallest to biggest in the y? Top to bottom or bottom to
0.
top?
It's bottom to top.
Got to start at the bottom and work your way up. You guys know that. That's life, right? So same thing here. When am I going to start hitting my y values? Not until I get to what?
-4.
Happens to be at 2 places, but that's okay. We will start at -4. Is it included? Is that y value on my graph?
Yes.
Yes.
Bracket all the way up to what?
0.
0.
Now, is it included?
No, it's not.
So this one doesn't count?
Well, it does.
Yeah, and that's what's tricky, right? You got to be careful. It is not here, but it is here. And so just like here, the -4 on my y's was included not once, but twice. But is the 0 included? Well, not here, but it is here. So we will include it here. So graphically, what did we hit? What x values? From -3, not including it, everything all the way to 1, including that. Those would all be represented for my x values. Those are what you could input and plug in. And what would you get out? Anything from what? -4 to 0, including both. That's what we are representing by writing that down. The domain and range. Okay. Now, in this text, they call them toolkit functions. There are many different types of functions that you guys have seen over the course of your experience in math. Some of the basics you should be able to graph off the top of your head just by looking at them. Okay, we'll review all that, but as we get further, the better that you can visualize where they are, what they look like, the easier it's going to be for you in calculus when you have to find certain things about those graphs. Okay, specifics. So one more thing we're going to talk about are piecewise functions. You guys may be familiar with one. It's called the absolute value. If you give me any number and I ask you for the absolute value of that number, anything, I'll put X to represent that. What do you do?
Take the positive and the negatives.
Okay, good. Now, not positive and negative for a number, but for a variable, you're right. So if I said find the absolute value of 3, what's the answer to that?
-3 and 3.
No, it's just 3. If I ask you to find the absolute value of -3, what's that?
-3.
3.
It's also 3. And this is why I'm bringing this up to you all, because you know the whole plus or minus thing, but you actually don't know what the absolute value definition is. It's very simple. It's 3 letters, 3 words. Distance from 0. That's what that means. Find the distance from 0. That's what the absolute value means. So when I put the absolute value of 3, how far am I away from 0?
3.
What about at -3?
3.
Does that make more sense why it's both positive and negative?
Yes.
But if I put find this, what is that asking? Find something that is a distance of 0 or from 0 of 3. And that's why you guys were giving me answers of, well, it could be 3 or -3. Does that make sense?
Yes.
Okay. All right. So that is what is called a piecewise formula or function. And hopefully you guys remember the graph of an absolute value. It does pass the vertical line test. So it is a function. It is not a one-to-one function though. So if I asked you to graph something like this, that is made up of 3 different functions or pieces, you have to know that I only use that x cubed function when I have things that are strictly less than -1. A -2, if it's between -1 and 4, and the square root of x function if it's greater than 4. Does anybody need me to review that at all?
Yes.
Yeah, okay. Let's do it real quick. I'm actually going to take that and move it over a little bit. All right. So if I ask you to graph this function, you already know it's a function. You know it's going to pass that vertical line test. We have 3 different scenarios here. One, this. So anything that's less than -1, I'm going to have that graph of x cubed. Now, hopefully you remember the x cubed. Looks something like that. The other graph that we're going to have to deal with is this one, which is called a constant. So if I graphed y equals -2, where is y equal to -2? There, for every x. And then lastly, the square root of x function. Do you guys remember what that looks like?
Half of a parabola.
Very good. On its side, it's that. Without this part. Because remember, square roots, we can't have the negative, so we don't get a negative out. So that's why the negative part is gone. And remember, it's a function, so it doesn't have that other piece. So these are the 3 functions that we're going to have to take and only use the x cubed, the pink one here, when it's less than -1, which means I'm going to get rid of this part of it, and I'm going to start here and only have this. Does that make sense?
Yeah, I was just wondering how the numbers worked with that
Got it.
and like what you did with the graph.
Open dot going down. The rest of that, I can go ahead and line out or erase. Try not to delete too much. All right. And then the next one was my blue one, but that one only went from what?
-1 to 4.
-1 to 4, excluding them. So now I have a open dot here, and it's going to be all of this all the way till I get to the 4, which would also be an open dot. Got those 2. And then the last one, only greater than 4, I'd have that square root of x. So I'd have to get rid of all of this part. And at 4, I'd have that open dot there and then everything else going that way. I'd have to go all the way to 5, 6, 7, 8, 9 to go up to 3. Because the square root of 9 is 3. So my final answer would look like that in the bright red. Is it a function? Yeah. It's really close to not being. Where?
At
-1.
-1 and 4.
At -1 and 4. If it was included at both of those, then it would not be a function. Could it be okay to include it at 1 and still be a function? Say there and there. Still pass, only hit once. You got it. Okay, so whether they give you this and ask you to evaluate f of 3, for example, and you find the output, or they ask you to graph it's easiest to just start by graphing each of these things individually and then just keeping the parts that they wanted, rather than trying to only do this part of that. It's where a lot of people will go wrong. Okay. On to 3.3. Anybody need a break? Are we doing okay? All good? Okay. This is probably the most important section that you guys are going to see to prepare you for calculus. All right. It is called rates of change and then attributes of graphs. A rate of change is a fancy way of saying slope. Because hopefully you guys recognize that slope is just the change in our y's over the change in our x's, which is what that means, those delta symbols, which we used to write as y2 minus y1 over x2 minus x1. Remember that? When we were dealing with lines way back in 7th grade, and we first started learning algebra and graphing the very first thing, which was line. This is that. Do you guys see it? The only difference is instead of having two x's and y's, they're just putting 1x and 2x and then using those to denote their y values. Okay. Why this is so important is because we will go into a lot of depth to go over how you can use slopes and rates of change, we call it, for real life. Okay, so all I want to make sure that you guys understand is that this is the slope formula. Nothing new other than the way that we're going to use it. That's it. Okay. Hopefully you also recognize that this looks very close to that example I did earlier. I'm going to write it a little bit differently. Do you guys see that? See how these things are the exact same? But notice if I did this, a plus h minus the a's would cancel out and we'd just be left with the h. That is that difference quotient. Really, really important stuff. Make sure that you guys work hard to understand it, not just get that homework done. Okay. So I asked, does it look familiar? If so, what? I already mentioned it. It's the slope formula for our basic lines. And how can we use this in real life? I wanted to give you guys a quick example, right? Let's say I went from my house and I was able to go in a straight line to Fresno City. Let's say it was 20 miles in distance. And let's say I rode my bike there. Are you impressed? Only person I can see is Barrett. And he's like, whoa, yeah, man, you rode 20 miles?
Farther than I'm riding my bike.
Well, what I didn't tell you, Barrett, is that I left last Tuesday. And what's my point here? What matters? Is it just the distance traveled?
The time it
It's the
took.
time. That's right. And so let's just throw out an easy number. Let's say it actually took me 2 hours. Now, are you impressed? It's up to you and your capability or your bicycle, right? Now, what I wanted to mention was a little thing called the distance formula. You guys remember that one? Now, what I want to do is I want to solve it for the time, or excuse me, not the time, the rate, which means I'm going to have to divide by time. And I want to find how fast I went. Because what would you guys say I went? 20 miles
10 miles an hour.
in 2 hours. Very good. And you know that we can go ahead and simplify fractions. So 2 goes in that 10, and I get 10 miles per every 1 hour, or what we like to say is 10 mph. Now, is that true? When I jumped on my bike, did I automatically start going 10 miles an hour all the way until I got to Fresno City and then stopped immediately? So what does that 10 miles an hour actually represent?
Your
The
average.
average.
The average rate that I traveled. Very good. And how do we get that? We just take the distance and divide it by time to get our rate. Did I probably go a little bit faster at points? Did I probably go a little bit slower at points? Yes, absolutely. But what this allows me to find is the average rate of change. Okay, so how would I do that? Well, I could just say that this is the 0.00 and this is the 0.22. And I could literally just find the slope of it by doing the change in my y values over the change in my x values. And we like to start with the bigger ones so that we don't have to work with negatives. So if I did that, I would then have this be first, and my y value with my other y value, and then my x value with my other x value. And if I wanted to flip it around to make it a little bit better, let's go 2, 20, right? So that I have my 20, which represented miles, over the 2, which was in time, hours. And you can see that the slope formula is just a rate. And you guys will expand and explore with that a whole lot more, not only in this class, a little, but a lot more so in Math 5A next semester or whenever you take it. Okay. So real quick, we're going to get to the attributes of graphs. What types of things would you want to know about a graph? What might be of importance to you? Just any old graph. What do you think? What would you want to know about it?
A couple points on there would be nice.
For sure. Like the whole shape, right? That'd be awesome. What else?
Input and output values.
For sure. Domain and range. So the whole look of it. Domain, range. What else? What about the look of it? Not just a couple points. How about any specific points that you guys might want to know about?
The midline.
The intercepts.
Good, good, good. Now we're getting there. Intercepts. Maybe the high and low points. We like to call the max and min. Maybe where it's going up versus where it's going down. These are all things that we might want to know, which we call attributes, specifics of that graph. So if I was able to give you a cubic function like this, x cubed looking shape, can you see where it's increasing?
Yeah.
And can you see where it's decreasing? Can you see where it changes from increasing to decreasing? Why that might be of importance. If you throw a ball up in the air, shoot an arrow or whatever, eventually it comes down, right? Even a bullet, it eventually comes down. Depending on the velocity and the angle that you threw it at, that's more physics stuff, right? And the conditions, then we can actually figure out if we know where it changes from increasing to decreasing, that point where it hit, we call it the high point, the maximum. Or if it goes from decreasing down and then goes up to increasing, that's going to be what is called a low point. Now, notice that it says local max and min. If you're local, what does that mean you are? From around here, this area, right? Now, some people say the Central Valley, some people say Fresno. Their idea of local is different. But locally, whether I draw it that big or this big or this big, locally, what is the highest point around here? It's that one. What's the lowest point around here? It's that one. But are either of those the absolute max or min from this entire graph? Is this the lowest point on the entire graph?
No.
No, Brian says, and I saw Barrett because he's the only one that I can see. He said maybe. And I like that answer because it depends on what's happening elsewhere. For this particular, Brian, you're absolutely right. No, because that arrow means what?
Infinity.
Infinity.
Goes down and to the left forever. So no, there's not going to be a low point. There's not going to be a global minimum or an absolute minimum. How about a maximum? No.
No.
But locally around this, yes, it is the highest point. So these are things that we're going to get into where we talk about locally versus globally or the absolute. Okay. So if you hear those terms, that's what we mean. So how can you find those maximums or minimums? We like to say maxima or minima for plural, where it changes from one to the other, whether it's increasing to decreasing or decreasing to increasing. And why are these going to be important? You'll find out in calculus. Okay, these are going to be those maximum and minimum values. And if this is the function of your sales, well, then obviously you want, if this is a profit chart or graph, you want to know how you can maximize them. What did we do right here? And you want to be able to find that. Oh, it's the best price is this. Okay, that's going to turn the most profit. That's what we'll do. So they pay people a lot of money to figure these things out. Okay. So here's the technical definition, which I don't like because it's very confusing. That's why I like to show you guys by graph. Okay. But it basically says that all of these y values are greater than these y values everywhere. Okay. And if it's decreasing function, then all of these y values are less than these on this interval. And that's how we can find these local maximums or local minimums based on how it's changing from increasing to decreasing, max, decreasing to increasing, min. All right, and those are going to be some things that you guys will learn in depth in calculus. Okay, so if I gave you guys something like this, can you find those intervals where it's increasing, decreasing, and those local max and mins? I'll give you a minute to try to figure that out, and then we'll go over it together. Right, hopefully you're able to look at that and think it through a little bit. What are the most important points? How many of them are there, first of all?
3.
Very good. They're so important, we're going to call them critical. All right. In calculus, we will call these 3 points the critical points or values. And what makes them so critical? What changes around them?
They either increase or decrease.
That's what's changing. At this point, it was decreasing until we got to here, then it started to increase. And then at this point, it was increasing and then it started to decrease. And then at that point, decrease changed to increase, which means what are each one of those 3 things?
Local.
Local maxima or minima. That's right. So help me out. Which ones are which? What is this point right here?
The
local
local
minimum.
minimum.
Minimum. So I will put at 1 comma -1, or they can just ask you for the X value and then not worried about the output. They can figure that out. What else?
The maximum is 3 and 1.
Good. Because locally around here, it is the highest point. It's not the highest point of the entire graph, but around that little neighborhood it is. And then how about the other point, 4 comma, looks like 1/2.
Local minima.
Excellent. Which means we just found all the X values that it should be separated for where it's increasing or decreasing. And what I like to do is just go one or the other, or you can go left to right. It's totally up to you. But let's just start out here. What is it doing from all the way out here, which since that's an arrow, that means indefinitely this way, right? That's all of this stuff. What is it doing here?
Decreasing.
So I'm going to say it's decreasing from
Negative infinity.
to what?
1.
If
Negative
one.
1.
Okay, very good. And we're talking about the X values. That's what we're providing them with, even though we're looking at the Y values that are decreasing, right? We're talking about the input versus output. So it's decreasing from negative infinity all the way to 1. That's what my Y values are doing. Now, how do I finish that? What do I put around the parenthesis or the infinity or 1? A parenthesis or a bracket?
Bracket.
Around what?
I think
The 1.
Okay. Everyone knows around either infinity, always parenthesis, no matter what. So that's good. Barrett even laughed because I slipped and said it. But what about the 1? You guys said to do this. Many of you. I couldn't hear everyone.
I think it's also a parenthesis.
Okay, now
yes, close.
I'm going to leave it blank for just a second and let's go to the next part. If we got all of this as decreasing, now what's this next part doing?
Increasing.
And where would you say it starts at?
1,
And it goes to what?
3.
Now you guys just told me to do this. But now you're telling me to do this. Make up your mind, would you? Is it increasing or decreasing at that value?
It's increasing at that value.
No.
Neither.
Very good. And that's why I paused. I just want to give you guys time to think. It's not doing either. How come? Well, look, guys, we're including it in both. You just going to choose your favorite? Just because you're a positive person, you say it's increasing? It's going up. It's going up. No. Remember, that's the critical point where it was what?
Starting to increase.
Yeah, that's right. It changed from decreasing to increasing. So can we include it in either or both? No. So that's a little confusing because it's not the domain that we're talking about. Because that would be included in the domain. It's a closed dot. But we're talking about increasing versus decreasing, and it cannot be doing both at the same point. That is the point where it changes from one to the other. Does that make sense?
Yeah.
Very important concept. So what are we going to do at 3? Are we going to include it? No, that's where it changes. And it changed to decreasing. So we got to unite from 3 to what?
4.
4.
And I'm not going to include either of those because I know that's where it also changes from decreasing to increasing. So I got to put another interval for increasing that starts at 4, again, not including it, and goes to
Infinity.
that's it. So hopefully those of you that already started looking at the homework, which many of you have, awesome job. Now this makes a little bit more sense as to why we're not including them, but yet we did for domain and range stuff. Okay. So what is the absolute max and min? What do you guys think is different? It's the absolute, excuse me, the absolute, meaning the entire graph, which means there's no arrow going up or there's no arrow going down because we know that does that forever. So there has to be what are called endpoints. So if I gave you this graph, could you find the local and absolute max or mins? And as you guys know, there may not be some of these options. What about the locals? Where should we be looking for those?
12. Oh, that's
16.
that's the absolute.
Good, there you go. The locals will always be found at those peaks and valleys, those humps in our graphs. So I'm looking here, here, and there. And obviously, how do we tell if they're local maxes? They're above everything. So I got one at x equals -2 and x equals +2. Or you can give me the actual points, -2, 16 and 2, 16. Okay, it just depends on the book on how they were going to want you to answer that. How about the local min? Well, we know right there at the origin in that little bubble, it is the lowest point. So at 0 for my x. But as Barrett and a few others were mentioning, how about the absolutes? Should I be including any of these as local? If I circle
No.
just like I did the other ones, can you see around that it is the highest or lowest point? Or could it
No.
keep doing this? Or could it hit there and go up?
No,
don't
it
know.
stops.
It
Yeah,
stops.
we don't know what it does, right? So we can't assume. So at endpoints, you cannot have local maxes or mins. But at endpoints, what can you have? The absolute highest or lowest points. And is this one anything?
No.
Unfortunately, no. That one's not going to give us anything because locally we don't know, and it is not the highest point, definitely not the lowest. But what about this?
Yes.
That is my absolute lowest point. So I will say I do have an absolute min at x equals 3. So is there an absolute max?
-2 and 2.
Yeah, very good. There's actually 2 of them at -2 and 2. That gives me the absolute highest marks on my graph. Very good. Very good. Okay, so just wanted to kind of walk you through that. And that takes us to our last section for today. And then we'll go into our breakout rooms and start working on our group quiz. Composition of functions. Now, this is something that you guys have already seen many times, I'm sure, in your math careers, but it's one that a lot of people still struggle with because of that weird little O. And that weird little O is just short. It's the symbol for of. This means f of g of x. Now, I much prefer, instead of that form, this form. I'd much rather you guys leave it as f parentheses g parentheses x, because you guys already know how to evaluate these. You know that you would work from the inside out. You'd plug in whatever they tell you to for x into your g function. And whatever you got for that, you would then plug into your f function. That's what we call these composition of functions for. It's just one function is made up or composed of another. All right? So just be careful. Make sure that you know that this little weird symbol is not the multiplication symbol. Okay? It's a common mistake. People, oh, I didn't even see it. All right? Be careful with it. I highly recommend that you take this form rather than this form. Okay? Get rid of that weird little O. So if I gave you guys an example with a couple of functions where I say, this is what f of x is defined as, and this is what g of x is defined as, could you find f of g of 2, f of g of x, or switched on you, g of f of x? Does anybody want me to go over any of those or anyone in particular?
Can you go with C?
C, you got it. G of f of x. Now, what I always like to tell my students is to take a step back. Look at the big picture. Don't get into the details just yet. And hopefully you see that this is asking you to do g of something. And remember what we talked about earlier. Didn't I already tell you guys what to do whenever there's a function where they ask you to replace the x's? Replace them all, everywhere you see them, with parentheses. Take out that weird x placeholder. Does everybody see that this and this are the same? I got g of something is equal to 3 times that thing minus 5. But what are they asking us to plug in instead of just x?
f of x.
Not just a number, but they want us to replace an entire function. And I just got done showing you up here what f of x is. So I will put in place of the f of x what it's equivalent to, which is 2x squared plus 1. And in order for you to then figure out what this is, g of f of x, we plugged in what f of x is to our g function, and now we're going to simplify it, which this was a pretty easy one. All it asked us to do was multiply by 3 and then subtract 5. So I'm going to get 6x squared plus 3 less the 5 will give me 6x squared minus 2. Don't make this stuff harder than it is, guys. Okay, that is not very difficult. This one is actually a little bit more challenging. Okay.
Let's see it.
Oh, I knew it. I shouldn't have said it. Move this to the side and give me some more room. All right. So this one, part B, says f of g of x. So again, big picture here. I got f of something. And I know f of something is equal to 2 times that thing squared plus 1. What did they tell me to plug in for that? G of x. which is 3x minus 5. So I have my f of g of x situated. Now I need to know my order of operations. And this is where most people make a mistake, and this is what I warned you already. It says to multiply by 2, and that's what a lot of people will do first. But remember, it's parentheses, nothing to do, exponents first. You actually have to square this thing before you can do the multiplying by 2. So I'm going to keep the 2. I'm going to figure out what all that is, and then I'm going to add 1. So if you need to go off to the side and do 3x minus 5 times 3x minus 5, go for it. I've been doing math for quite some time. I'm pretty good at it. I know that that's going to give me my 9x squared. It's going to give me my positive 25 at the end. But to get that middle, I'm going to have negative 15x twice. So that's going to give me negative 30x. Then I'll go ahead and distribute. The 2, which is my multiplying, to all of that, which we expanded. So now I got 18x squared minus 60x plus 50 plus 1. If you guys are cool with it, I'm just going to do that now. And that, my friends, is what f of g of x would be.
How we do A then? How you add 2 from A?
Yeah, so that's actually nice that we did it this way. You're going to do the same thing, but instead you would do g of 2. You would plug in the 2 to your g function. And when I plug in 2 there, I'd get 6 minus 5, which is 1. So now I got f of 1. And now I plug the 1 in here and square it, multiply by 2, and then add 1. So I get my answer is 3. Or since I already found f of g for any x, they want me to replace the x with 2, I could just plug it in here and here, and I guarantee you guys I'll get the same thing. Let's check it out. 18x squared minus 60x plus 51, and they wanted us to replace it with a what?
2
Replace what with a 2?
x.
Everywhere you see it. So careful, 2 squared is 4 times 18 is 72 minus 120 plus 51. 51 and 72. 123 minus 120. There's your 3. Math is pretty cool because there's not just one way to do it. So the last thing I want to get to today is how do we find and put it all together, the domain of a composite function? Well, just like we evaluated it, we got to work from the inside out. So all this is saying is if we have a domain of a composite function, we're going to find the domain of g first, and then we'll take that and find the domain of f next. And basically, after we found the domain of each of those, we're going to make sure that we can find if there's anything that we need to exclude from G that's not going to be in the outer f function. All right. So sometimes we will have something like this where they're going to ask us to figure out what they're calling f of x. Can you rewrite this as 2 functions? So can somebody tell me what these would be if f of x is equal to g of h? What did I tell you guys to always look at? The little details or the big picture?
Big picture.
Good. And if I'm looking at the big picture, I'm trying to find G. What would be the big picture here? What do you definitely see? That's what I see. 4/3 minus something. And that something is the details. So what I'm going to put is either the square root of x, or I can just leave it as x. Because then what would I have to replace that x with in order to get this final product?
Square root 4 plus x squared.
Very good. Excellent. Now remember, if I already have the square root here, I don't need to put it here, because all I would do is put this in place of that, and that would give me my original function. Now, if you don't want to have that and you just want the x, then yeah, you'd have to have it there. Either way would suffice. Okay, so that's it. I know there was a lot. There was 4 sections. I wanted to make sure I gave you guys a good base, a good start to the class. So I'm going to go ahead and stop the recording now.